Okay, I'm going to go over how to use this solubility table with an example. And this will be from yesterday's lecture. Now, if you haven't looked at that lecture yet, this may not make a lot of sense. But the main thing I wanted to do was to show you how to use this handout. So let me see if I can find it electronically. Also, I changed um, the lab schedule. So download the new version is 4.1. So make sure you download that. And I substituted in a dry lab for another dry lab because you need practice on doing what we're doing today, stoichiometry. So make sure you look at that. I sent a message out regarding that as well. Okay, so to use this solubility table, you need to know the cation and the anion. Okay. And what you do is where they come together, if it's white, nothing happens. If it's black, a solid forms. The fancy word for solid is a precipitate. So for example, when we put sulfide along with iron, so we have iron sulfide, it's a solid. Potassium chloride, white, it's nothing happens when you mix it. That's all there is to it. Now, when you take your next chemistry class, they may or may not allow you to use this. They may want you to know the rules, and I have the rules down here as well. You've kind of got the best of both there. I think the table above is more straightforward than these solubility guidelines. And basically, that's how that table was created, based on these guidelines. And some teachers are very anal about making you memorize this, and others are more flexible. It just totally depends on who you have. I don't like for you to memorize stuff like this because you have a smartphone and you can look it up in 2 seconds. So why memorize it? But, and you'd think because I'm so old, I'd be doing the old school ways. Not me. All right, so are there any questions about how to use this? It's just really easy to use. And I've been, this is the latest one. I've got quite a few of these. If you go online and do a search on solubility tables, and I found this one the most straightforward, black or white, boom. So if you had something like, now double replacement reactions basically are, you take two solutions and dump them together, and then something may or may not happen. And what happens is the cations swap. So there's two new combinations, and then two new combinations could be like, and then you have to determine whether it's AQ or S. Okay, the AQ is going to be nothing happens. That means aqueous. The S is going to stand for solid. Also, depending on your teacher next semester, they may have you do PPT, which is short for precipitate. Just depends. In this class, you can use either one. They mean the same thing. So, okay, so you go sodium and chloride. So we go, here's chloride, and there's sodium. white. Means nothing's happening with that combination. We just looked up the iron and the sulfide. Sulfide and iron. So that's going to be an S, and this is going to be an AQ up above. And that's all there is to it. Now, in some ways, double replacement reactions are easier than single replacement, because all you do is you have the new combination and you look it up on a table. What's hard about the double replacement is you've got all these little equations you have to do. And the equations aren't hard, they're just a ton of detail, and it's easy to leave out a detail here and there. But they aren't hard, they're just very detailed focus. Okay, so straightforward enough? Okay, so I'm going to all right. This is a fancy word for what the rest of this unit is going to be about, stoichiometry. And who has heard of stoichiometry? Anyone? A couple of you. Okay. It's simply the mathematical relationship between products and reactants. And because I spelled Molar wrong. Okay, so it's a molar relationship. That's why we spent all that time learning how to convert grams to moles, liters to moles, number of particles to moles. It's moles, moles, moles. Okay. This is a very weak area for incoming 1A students and 2A students and 3A students. So we're going to spend a lot of time on this. The dry lab that I swapped out for you is on stoichiometry, just because you need lots of practice. The dry lab that I substituted for was on gas laws, which is not stressed at all. So that's why I swapped it out. I just want to make sure the weakest link in your next class is going to be stoichiometry. So I'm going to make sure you really hit it hard. Okay, so let's look at a typical stoichiometry problem. So I want you to remember now, we've got 4 steps all the time. So balance equation if a reaction happens. Not all the time, but in classic stoichiometry, reaction always happens. So these 4 steps are for sure you need when you're talking about a stoichiometric problem. Then what's given? To sound familiar, what are we trying to calculate? And then the setup. Now there's going to be one extra step in this that you're not used to. And that has to do with the balanced equation. So let's look at a equation here. Let's look at Okay, so we're going to take methane and burn it. We're going to get carbon dioxide and water. And let's see. Okay, if 34.5 grams of water is formed, how much oxygen gas was used? So this is a very straightforward stoichiometry problem. It's in 3 steps, the setup. Step number 1 is balance equation. Okay, is it balanced? No, it's not. So let's, okay, so we have 1 carbon, 4 hydrogens, 4 hydrogens, 4 oxygens, 4 oxygens. Okay, it's balanced now. Now it's crucial, I want to emphasize this, it's crucial you balance the equation correctly, because there's going to be a ratio of the coefficients from the balanced equation in the middle step. Okay, and remember, balanced equation is a molar relationship. And a molecular relationship. So we can't do anything with oxygen gas and water unless we're talking moles. So the first step is get us into moles. So we start with 34.5 grams of water. I'm going to get that over to moles of water. So the grams got to cancel. And there's 18.02 grams in 1 mole of water. Now, does everyone know where I got the 18.02? Okay, periodic table decimal numbers. Add them up. 1 oxygen, 2 hydrogens, 18.02. Okay, now we have moles of water. Now we get to figure out how many moles of water, moles of oxygen. Okay, that comes from the balanced equation, the coefficients. So water has to cancel. And we're trying to calculate oxygen. So we look at the coefficients. Okay, it's 2 to 2. So this is why we balance equations, for that coefficient ratio. Okay, now we have moles of oxygen gas. We want grams of oxygen gas. So we need to convert now over to grams of oxygen gas. Okay, so, and it's 3 sig figs, 4 sig figs, 3 sig figs. So our answer is going to be 3 sig figs. So we've got 34.5. Now, do you have to put 2 over 2 into your calculator? No. You can if you want for your OCD folks, but you don't have to. Adam, you have a question? That's the oxygen gas. Oxygen is 16 apiece. So the way I did this in my calculator, I went 34.5 times 32 divided by 1802. Enter. Also, I didn't put 32.00 in. I just put 32 in because your calculator assumes that. Okay. Now, I'm going to tell you something. And I don't know if a lot of teachers tell you this, but this is important. Every stoichiometry problem, did you hear that? Every stoichiometry problem has these three parts: mole conversion, coefficient ratio, back to what you're trying to calculate, conversion. Now, when you do the dry lab, called dry lab 7, or whatever our lab number is today, STOI, STOI, you're going to do a whole bunch of stoichiometry problems. And when you look down, when you're all done, you're going to notice that they all look like this. So the pattern is the same. Convert to moles. Well, if you start with liters, what do? Liters of gas. You got to get it to moles, right? What do you use for liters of gas? 22.4, yeah. So this conversion is going to be, I'm going to do one in a minute, but this conversion is going to be 22.4 liters. So the liters cancel. What if I said you got 4.5 times 10 to the 23rd atoms or molecules of water? What is this first step going to be here? Avogadro's number, 602 times 10 to the 23rd. So get it to moles first. So that's your first task. Then look at your balanced equation, look at the coefficients, and then convert to whatever you're trying to calculate from the moles every single time. Okay? So I'm trying to get this pattern idea in your head. Then you just need to practice it 600 or 700 times. But seriously, you need to practice a lot. And you'll just, after a while, it's the same thing every single time. And if you learn like me, repetition. Okay, so let's do a bunch of example problems. Are there any questions about that? Where I got the numbers, how everything canceled out, all that good stuff? Okay. All right, now let's use the same reaction so we don't have to keep balancing it. So we've already done step 1 with this problem here. Okay, so if 45.6 liters of water vapor are formed, how many liters of oxygen gas was used? Now, as soon as you hear gas, 22.4, assuming it's at standard temperature and pressure. It doesn't have to be, but it makes things easier if it's at STP. Now, if you're taking 1A next, you'll rarely use STP conditions because they want you to learn the ideal gas law. But in Chem A, we use STP. Okay, so Balanced equation. It's already balanced. Number one, what's given? Now you can do this via parentheses as well. I like to use, this is called railroad tracks. A lot of your teachers next semester will use railroad tracks. Some of them will still use parentheses, but they'll accept, if you like parentheses, use parentheses, and they'll most likely accept it. Some of them may not, and I may not. Okay, since we're talking about gases now, we need to get over to moles. So we're using 22.4. And now we need to look at the ratio of, and it's going to be the same ratio of water to oxygen, 2 to 2. So this is from okay, so this first step is always, always take the given, convert it to moles. Always, the middle step here is the balanced equation ratio of the coefficients. Now, when you balance the equation, let's say you had doubled everything. The ratio is still the same. Like 1 over 2 is the same as 2 over 4. It doesn't matter. So some of your teachers next semester may want you to reduce, if there's a multiple, a common multiple throughout all your coefficients, may want you to reduce that down. It just depends on the teacher. But the reason you balance the equation is this ratio. And my take on this is a ratio is a ratio. 1 over 2 is the same as 2 over 4. So when you balance the equation, as long as it's balanced, it's fine. Then the last step is getting you to what you're trying to calculate. In this case, we're looking at liters. Okay, now look at everything now. We have cancel. Liters cancel, moles cancel, water cancel. So we're left with liters of oxygen gas. And what are we trying to calculate? Liters of oxygen gas. This you didn't even need to use a calculator. Why didn't I need to use a calculator on this? Okay, we had 2 over 2, right? That's just 1. And then notice the 22 in the bottom here, 22 is in the top here. So that cancels. What are we left with? 45.6. But it's not always going to be like that. Just happenstances. This happens this way. Okay, so let's do a few more examples here. Are there any questions about this one? Yeah, exactly. Yeah, from the balanced equation. Yeah, exactly. But if you're going from gas to gas, the 22.4 always cancels though. It's the ratio that's going to be different. Ollie, does this make sense? Let's use the same methane equation. So how many molecules of carbon dioxide is created if 34.5 liters of water are created? Okay, so is the equation balanced? Yes, already balanced it. Step number two, what's given? 34 liters STP of water, and we're trying to calculate how many molecules of carbon dioxide. So how many? Whenever you hear how many, think Avogadro's number. By the way, did anyone get snow today? Because it was supposed to go down to 4,000. Is anyone above 4,000? Anyone above 4,000 feet in here? Okay, so we're starting with 34. Okay, so we need to get what's given to moles. So again, 22.4 liters. Okay, so that gives us the liters cancel, gives us moles. Then from our balanced equation, we need water and carbon dioxide. So, so that's water's 2. Okay, so now we have moles of carbon dioxide. Now we need to go to Avogadro's number because we want to know how many molecules. Okay, so now we got molecules of CO2. Everything else cancels. Okay, did everyone do this calculation? And those of you who did do it, did you get the same answer I did? So this is the way I did it with my calculator. I went 34.5 times 6.02 EE 23. Hit the divide 22.4, divide again, 2, enter. So there's 2 numbers on the bottom. You hit the divide key twice, 1 for each one. So make sure you do that. Okay. A lot of people, they'll go, well, it's 2 times 22.4. No, it's not. It's in the denominator. So it's not 2 times 22.4. Okay. Did anyone not get that answer? It's 44 out and it's noon. It's a little different weather than 39. I mean, 39 on Thursday. My temperature was 91 in Natomas, and we're down to 44 today. Okay, I'm going to do one more problem that's has a slight nuance to it. So how many kilograms of carbon dioxide is produced from 23.4 liters of oxygen gas? Okay, so we've already balanced step number one, balance equation. So we're looking at 23.4 liters of oxygen gas. Now, in your reading and in your next semester class, they're not going to say oxygen gas, they're going to say oxygen. Oxygen is never by itself, it's always in gaseous form. So that means automatically you write down O2. Here, I always say oxygen gas, nitrogen gas, helium, hydrogen gas. So there are 7 chemicals that are called diatomics. Okay, and you're probably gonna have to memorize these next semester. Okay, and that is so if you whenever you see hydrogen, hydrogen twice. Whenever you see oxygen, oxygen twice, etc. Okay, 23.4 liters starting with. And we need to convert that to moles. So we need the ratio of CO2 and oxygen. Okay, oxygen's 2. Next thing we need to do is get carbon dioxide, moles of carbon dioxide to grams of carbon dioxide. Then we're going to go from grams to kilograms. Okay, basically I've done every combination of stoichiometry problems you're going to see. Now, there is an advanced stoichiometry, like always, and that's called limiting reactants. And I'm going to show you that. Okay, there's going to be an extra credit problem on test 4, limiting reactants. Okay, but it's extra credit and it's a little more involved than this. In fact, what I think I should do is do that Friday, not today. Okay, what I want you to do is practice this between now and Friday, because limiting reactant problems, it's got 3 of these plus a subtraction problem per problem. So you need to understand this first really well. So if I do this now, it potentially could confuse you. Okay, yeah. The 202. Oh, there's 16 apiece. So actually it should be 32.00, not 3201.
No, on the railroad track.
Here?
Yeah.
That's from the balanced equation. So go back up to your balanced equation in your notes. Right here.
Okay.
Oh, you didn't balance it yet.
Oh, this was from the big. This is that last.
Yeah, I know, but I
Oh.
use it's the same equation though. So let me balance it real fast for you.
This one right here.
Oh, yeah, it's already balanced. See the 2? That's where it comes from.
So this equation is used for all these problems.
Yes.
Okay, okay.
Yeah.
And for like every future one we're doing in
No, it
this?
depends on what the problem is. I just use the same one each time, so we don't have to keep balancing it.
Okay.
Better? Remember now, ask questions. Okay, so that's what I wanted to cover today. And I would like you to practice these. And a good way to practice it is to go and pull up the your dry lab. Are there any questions on this last one? Remember I said there's always 3 steps? Unless you're doing an additional conversion, there will always be 3 steps. This one's step 4 because it was the additional conversion. Okay, this dry lab STOI. STOI is short for stoichiometry. And if you download the new lab schedule, you'll see where that fits in. But if you want to practice balancing equations, this is a really good one. Yeah. I need to look at this. I forget the numbers. I know the titles. Oh, no, you can do that one too. No, the one you're going to is the gas lab. You have,
Are we doing this lab today? The
No.
stoy?
no, I'm
Okay.
saying if you want some extra practice.
Oh, so we don't have to do lab stoy.
No, you do on the schedule when it comes up.
Okay.
But I'm saying you can do it now instead of then for extra practice.
Next Saturday.
Yes, it's going to be the double replacement lab.
And then you said you would post the data table. For
Yeah.
the double
Mhm.
replacement lab.
Yeah. Who's going to send me an email?
I'll look
Okay.
up.
Okay. Thank you. No,
Have two labs.
no, you never have 2 labs. So let me pull up the schedule. Let me show you what we're doing. Now notice on this general information, it says 4.1. The old one was 4.0. So, so next week is a wet lab, lab 11. So we're doing a stoichiometric, or we're doing a stoichiometry lab. And net ionic equations is related to double replacement. And that you can do at home anytime. If you look at the video from yesterday, I'll talk about net ionic equations. So it would be the week after next when officially we do the dry lab stoy. But you can do it between now and Friday just for practice. You have to do it anyway. Yeah. Dry lab 9. No. Yeah, but you don't have to, the dry labs you can do, that dry lab you can do at home. Don't do it on the same day as that lab. It's homework, yes. Let's really knit it out here. It's homework. Yeah. Graded homework at that.
So it's still try to still on the 27th, the week after.
Yeah, I always give you a week. Except for the very last lab. That's a 2-week lab. Okay, so pre-lab for stoichiometry needs to be done. The net ionic equation is related to double replacement reactions.
That's a good thing.
Yes, I may kick this up a week. The reason I want to kick it up a week, it's for I want you to get test 4 down pat for stoichiometry. It's real important. Yeah.
Yeah.
Oh, correct. Yeah. Yeah, that's finals week. They don't have finals week here. They have finals week at Sac City, but not here. I don't know why. So yes, because the 17th is commencement, and they don't want me doing anything that day. And then the next day is the semester's over, and they don't like me doing stuff that day either. I mean, everyone else is already done by then, except for there's 2 of us that teach. There's a 2A class that is taught on Friday, Saturday as well. In fact, a lot of my Chem A students from last semester are taking that one. So yeah, so it's all home stuff. Yeah.
So the practice test number 4 is this the official one that's on the test related files?
Let me double check. Her question was, it's under files test related. Okay. I'm glad you brought that up. Yes, that's perfect, actually. So the lab 4 practice test posted is a really good practice test. Yeah. I can't hear you. What? No, that's the final, which has test 5 embedded in it. So you have another in-person test, test 4, and then the last week you're gonna have an in-home test. Okay. The next test you're gonna have is gonna be in here. Yeah, and then the last one will be at home. Okay, this practice test is a really good test. Yeah. Uh-huh.
The hydrate is due tonight.
You should have all the information to do all the calculations. Yeah, because it's just doing grams to moles and all that. Yeah, it's really. Yeah, you should be more than. And then next week's lab, wet lab is on stoichiometry. So it's a real stoichiometry lab. So, and again, you will be more than well prepared for that. All right. So again, today's lab, yeah. No. Send me. Right. Send me an email. I'll post a key for it. That's a good question too. I'm glad you asked that. So today, for those of you who would rather take the data set in today's lab and do it at home, you're more than welcome to. I've already extended that to the Friday folks. It's a fairly short lab anyway, so it's up to you whether you want to do that or not. Okay.
Table where you just go from.
Hmm?
Did you say like this is just like a multiplication table? So like you just go
Yeah.
you find out like
Yeah,
okay.
where they meet. Yeah.
Okay, no.
White, nothing happens. Black, there's a solid
Yeah.
form. And it's based on the rules I gave you there. That's because it's a gas. All gases are 22.4. That's standard temperature pressure, STP. And it doesn't matter what the gas is.
Doesn't matter what the gas.
Correct. Right. Now the grams, though, you have to go to the periodic table and the molar mass. You have to add up all the decimal numbers. So that's specific for the molecule. The gas is not specific, and Avogadro's number 602 times 10 to the 23rd is for anything as well.
Okay.
So the only one that's real picky is the grams one. Sure.
So today's flying version at home, or
Right.
so is it an easy one?
Oh, it's not. Yeah, it's kind of like last week's slide. You're going to be adding two chemicals together, and either nothing happens or a solid
But
forms.
that shows us if there's a reaction. Okay, and then where can we find that in the?
When I post it.
Okay, perfect. Then I have a question. Let me get my